So let us define the character of a group. The character of a group is a homomorphism chi. So this chi acts on G, and you land in the multiplicatively closed group of a field. So that is f star is f minus 0. So this f is a field. So notice that this chi, you can think of it as a function acting on G, and this function is a homomorphism. So the theorem we want to discuss in this lecture is this: linear independence of characters. So say you're given distinct characters chi1, chi2, chi-n. So all these are homomorphisms acting on G and they are distinct. Then they are linearly independent. So distinct characters are linearly independent over F. So recall that linear independence means that we do not have a non-trivial relation. So not and null, there are two negatives here. So we do not have a non-trivial relation like this: a1 chi1 plus a2 chi2 all the way to an chi-n equals to 0, where each ai lies in the field. So this non-trivial relation means that all the ai cannot be simultaneously 0. So basically what we are trying to say is that you have chi1 to chi-n, there are these distinct characters and they are linearly independent. If you have an equation like this, then this can only happen if all the ai's are 0. So to prove this theorem that distinct characters are linearly independent, we will choose the method of contradiction. So you start by assuming that the characters are linearly dependent. So if they are linearly dependent, then there is some minimal m. So there is some minimal element m here, so that you get this equation. Because if they are linearly independent, you cannot have this equation. The only case you have this equation is when these ai's are 0. So since they are linearly dependent, you have such a non-trivial relationship. So there are a bunch of ai's which are not 0. So there are some ai's which are not 0, and you take the minimal m. So the idea is that, from this m we will come to a non-trivial relationship between characters which will have m minus 1 elements. So if it will have m minus 1 elements, then we have contradicted the minimality, because we are saying minimal is m. So that is what we want to show. So we start by choosing an element G prime, this element G prime in G, in our group G, such that chi1 of G prime is not equal to chi-m of G prime. So this is obviously possible because all these chi are distinct. So at least on one element of G, they should act differently. So now, so notice that you have G here. This chi1 is acting on G. This chi-m is acting on G. Instead of G, you act on G prime of G. So we have done nothing. You have taken this equation and you have multiplied by G prime G. So instead of G, you are writing G prime G. So obviously now you use the homomorphism property of chi1. So because this chi is a homomorphism, so this factors as chi1 G prime times chi1 G, and this chi-m G prime times chi-m of G equal to 0. So this implies this by the homomorphism property of our characters. So now we multiply this equation right here, say equation 1 here, this entire equation by chi-m of G prime. So I'm multiplying this by chi-m of G prime. So you get a1 chi-m of G prime, you put in chi1 of G as such. So this thing remained as such. In between you're putting in chi-m of G prime. So multiply everything by chi-m of G prime. So you take this, you get this and this, and then you get again chi-m of G prime. So denote this equation by A and this equation by B. So now A minus B. So you can immediately say that these two terms, this and this, will cancel out, and you will just be left with m minus 1 terms. So you can see this now, chi-m of G prime minus chi1 of G prime, and the other things are just constant. I mean, they're the same. This and this, these are the same. So these can factor out. So this minus this, and then you have a1 and chi1 of G. So similarly for the second term, you will have chi-m G prime minus chi2 G prime a2 chi2 of g all the way to this place, chi m of g prime minus chi m minus 1, because this thing is just cancelled out. So you will only stop at m minus 1, m minus 1. So you have m minus 1 here equal to 0. So notice that there are m minus 1 terms because the mth term has cancelled out. So this contradicts our minimality because we said the minimal was m right here. Now important corollary to this theorem is that, say you have phi 1, phi 2, phi n are distinct embeddings of a field k into field f. So embeddings are nothing but these injective maps. K is getting injectively embedded into f. So this is an injective map. So like this. So these are distinct embeddings. So then these embeddings are linearly independent as functions on k. Obviously these embeddings are functions on k, so they are linearly independent. Or in other words, you can say automorphisms of k are linearly independent over k. So again, say for phi 1, you have to just show that these are characters. So this phi I are characters. So to show they are characters, we have to tie it with this definition here. So obviously f star is a field, so this side is good. This side you set this as a group. This is a multiplicative group, k star as g. And then the only thing we are missing here in the automorphisms is 0, but then just put 0 maps to 0, because here f star is multiplicatively closed field f minus 0. This is also multiplicatively closed field, so k minus 0.